Screen visible irukka? Can you see the screen?
Not yet come,
Kavin
sir.
Kumar, can you mute your...
Nagarajan, sir. Kavin Kumar, please mute your audio. Kavin. 18118 Kavin Kumar.
Kavin Kumar? Kavin Kumar?
Done, sir. Done.
Can you guys screen?
Yes, sir. Now it is visible.
So in the... So in the last class, we started construction of auto transformer, and I just gave you the brief introduction about its working principle. And we will continue the same from the beginning of it. And an auto transformer is a variable AC transformer. Unlike two winding transformer, it will be having a single winding that itself will act as primary as well as secondary. Okay, so it is wound on a single core. A single coil is acting as primary and secondary. It is based on our choice where to keep the center tapping to get a required amount of voltage. Okay, so look at this diagram. This is a step down auto transformer. So the point C, which you are seeing at here, is movable. This point C is movable. You can move this point anywhere you wish. Okay, I'll show you a practical auto transformer at the end of this session, so that you can see. You would have seen that in the machines laboratory, and I'll show you how to use that at the end of this session. Okay. So this point C is movable. Already we have studied in the first unit that based on number of turns, the load will be receiving a voltage, isn't it? So for example, if a transformer's primary is more in number compared to secondary winding numbers, turns of secondary, then the transformer is called as a step down transformer. That is, primary winding will be having more number of turns, secondary winding will be having less number of turns. For a step up transformer, the primary winding number of turns will be lesser compared to secondary winding number of turns. So based on the number of turns, the voltage ratios differs. Okay. So here in an auto transformer, these numbers are not fixed. The number of primary turns and number of turns in the secondary is not fixed one. We can change it ourselves manually. Okay. So this tapping, the point where C is provided, is called a tapping point. This tap can be moved by means of rotating a knob or something, whichever is given in the auto transformer. So just by adjusting this, I'll change the number of turns. For example, assume if I put the tap at this point, this much number of turns will be connected. So here I was only now of turns is load side. Okay, so what respectively the voltage at this load side will be increasing. Okay. But what is happening in the primary side? The steering is assumed to be primary turn. Okay, so in no case the number of turns in the secondary exceeds the number of primary. Okay, so the entire winding is assumed to be primary. The reason is the supply is given across the entire winding, isn't it? So in a parallel circuit, the voltage will be equal. So what you are feeding here as supply voltage, for example, I'm feeding 230 volts AC. So I'm applying a 230 volt AC that appears entirely across the total winding from A to B. Okay, so point A is assumed to be primary winding. C is assumed to be secondary winding. Okay. So this part we derive show how much amount of copper is saved. I explain the difference between auto transformer and an ordinary. The first point is an ordinary two winding transformer will be having two different windings, namely primary and secondary. They will be having different number of turns. Okay, so that is one difference between two winding transformer and auto transformer. The second one is the voltage of two winding transformer is fixed. So for example, if I have a turns ratio of 200 is to 100, this ratio means number of turns in the primary and number of turns in the secondary. Okay, so I'll denote that as NP, and the secondary number of turns is denoted as NS. Okay, number of turns in the primary is 200, number of turns in the secondary is 100. So what type of transformer is this? So this is a step down transformer, isn't it? So step down transformer means the load side voltage will be halfly reduced. The ratio is half. V2 by V1 ratio is 0.5. So the output voltage will be half of the supply voltage, isn't it? But in an auto transformer, this number, the number NS, is not a fixed one. Though NP, the number of turns in the primary, is fixed, NS is not a fixed one. So we can get a desired output voltage at the load side. Do you understand? So the secondary side voltage is set based on the user application, and with respect to that, we will be getting supply voltage. Okay, and look at this point. The winding AB has a total number of turns N1 in the side, and B is considered to be secondary. That is what I told you in the previous slide. The total windings A to B is considered as primary winding. The number of turns between C point and D is considered to be secondary winding. Okay. So whenever I apply voltage across B, A and B, so for example, the same example I'll tell you. The supply voltage is 230. So what will be the voltage that appears across A and B? Can anyone answer? I'm applying 230 volts across the supply source terminals, phase and neutral. This is the phase point and this is the neutral point. Okay. So between phase and neutral, I'm applying 230 volts. What will be the voltage across AB? VAB. Can anyone answer? Voltage, very good. The voltage depends because they are connected in parallel. So what is the voltage across B and C? How you know this? I'll show you the answer. 230 is the answer for this question. could can you hear? Here, Venkatesh? Okay. So the voltage across A and B terminal, you wanted me to repeat, so I'm repeating it again. Don't get bored. The terminals between A and B, they are connected exactly across the supply voltage. Okay. So whatever you give a supply here will appear across this terminal. That is what we have written here. VAB, that is the voltage across A and B terminals is same what you give from the board supply panel. So if I have given reduced voltage from the panel itself, I get the reduced voltage across A and B terminals. Okay. So I am asking now, what is the voltage across B and C terminals? That is the terminals connected across the load. Look at here. The terminal as phase of load and neutral of load. So these two are connected. The terminals B and C are connected across load terminal. Okay. So what will be the voltage I receive across the load, which is denoted as V2 in this picture? I asked you that as BC. Okay. So usually we will write a transformation ratio equation as V2 divided by V1. That is secondary voltage divided by primary voltage. Secondary number of turns divided by primary number of turns, which is equal to the transformation. So these two ratios are equal. That is what I'm meaning. Okay. So I know what is V1 supply voltage value. I know, which is VAB given as 230. So I asked you what will be V2. So what will be the answer? Can you answer me now? So VBC could be so I should cross multiply this here. V1 is nothing but VAB. So I'm writing that as VAB into N2 divided by N1. Can you guys see this? Do you understand now? Anyone answer me for this question? At least, do you understand or not? Okay. So if you want to measure voltage across these two terminals, you should be using this formula. Otherwise, we can write it as V1 into N2 divided by N1. Okay. So that is what we have given in the next slides. Before going to that, I should measure voltage across each turn. So for example, Let us take the same example. We have the number of turns across A and B terminals are 230. So n means number of turns. Okay. So number of turns across A and B terminals are 230. And supply voltage, which is given as VAB, is also 230. So my question now is, what will be the number, the voltage per turn in every winding? Okay. So total number of turns is given as 230. Supply voltage is given as 230. So what will be the voltage per turn? The question is, the answer is there in the question. Voltage per turn. The voltage value is 230. Number of turns are 230. So we will get 1 volt. Yes, very good. So to find out that, we will use this equation. Number of the supply voltage is given as V1. Number of turns is in the primary side is given as N1. So in the primary side, the voltage per turn. Look at this last line of the slide. Voltage per turn in this winding is V1 divided by N1. Similarly, the voltage across second terminal. That is what we derived in the previous slide. The voltage across the second portion of auto transformer, that is the voltage across load terminal, this point, from this to this, which is denoted as V2, will be V1, what is the supply voltage, into N2 divided by N1. So that is called as V2. So we know that transformation ratio K is nothing but V2 divided by V1, N2 divided by N1. So instead of these terms, I can rewrite this equation as V2 is equal to K into V1. Can we write this equation like this? Since V2 is equal to V1 cross N2 divided by N1. So N2 divided by N1 is considered as K, which is the transformation ratio. Okay. So that value is substituted here. I'll get V2 is equal to K into V1. Do you understand now? So that is what given in this line. And let us see what is happening to the current values. So better and for better really understanding auto transformer, you just imagine a bottle filled with any liquid. For example, you just imagine a water bottle. You have a bottle like which is filled with, okay, and you make two holes at here. Sorry, you make a hole at this point. Initially, it was filled with water. Okay, so the water drops out. What you get is only this portion. Okay, so similarly, you have a full voltage from this point to this point, out of which you are selecting only this portion from this to this. Similarly here, look at here, you will be getting a water up to this portion only. So if you want to making a hole at this point, at the bottom of the bottle, isn't it? If you make a hole at here, you will be there from this to this. So this much amount of water you will be getting. What the simple theory behind it? If you want more amount of voltage at the load side, you should make center tapping this one. So when N2 reaches and the number of turns in the secondary comes closer to N1, we will get the maximum amount of voltage at the load side. Okay. So let us see what you. So when on play, amount will be considered to be I1 is the total current that is passing from the source. For example, I'll give you an example. Let us imagine there is no load is connected. Initially, the open. What will be the magnitude of I1? Can anyone answer? Not I1. I'm asking what will be the current passing through? There's the current magnitude of current I. The load is kept open. I'm asking the question is what will be the magnitude of I2? Zero. Why? The reason is the current will not pass through open circuit. Okay. So at that time, will there be any current passing through I1? Sorry, the windings. I1 will have any value, or that will also be zero. I will be zero because the current not I that is called I. Okay. So in the let's here.
Nagaraj sir, sir voice is breaking. Hello?
No, excuse me.
Can you hear me now, man? Is it audible now?
Okay, yes.
Oh,
Yeah,
okay.
yeah, it's audible.
Yeah, the network is poor here.
Can you see the slides?
1 second. Actually, now only one Nagarajan is available.
Okay.
Yeah, now it is.
Is it visible now, ma'am?
Yes.
Okay.
Okay.
Okay, ma'am. Thanks. Okay. I have connected a part load with suit.
Sir, still it has some problem. Voice.
Okay. Now, is it now?
It is breaking. It is not continuous.
Okay. I think I have some issues with my internet. Oh, ma'am. Is it now?
Now also, sir. Is it okay for others? Only for me. You please
Excuse me,
message
one
in the
minute.
chat box, guys.
Is it audible now?
Okay, fine. Okay.
Any so
No, while I started speaking,
later on.
the first. Hello.
Yes, ma'am.
Again, the problem.
Now, ma'am.
It's okay.
Is it okay now?
Yeah, it's okay.
But when I speak, the voice is breaking.
Yeah. When you are going to the slides, it is started breaking. Okay, you may proceed, sir.
So when load is started, so based on, for example, if you have three of current.
No, sir. No.
Connected.
Again, problem, sir.
Okay. Hello.
Hello.
Ma'am, is it audible now?
Yes, sir. Now, when you are asking, it is audible, but once it is started taking classes, it is not
While
audible.
taking, okay. I have tried a different headphone now.
Okay.
Okay. Auto transformer struggles now.
Yeah, it is. You may
Okay.
proceed. Yeah.
Okay. So when load is connected, the current is splitted, and current passing through the load. The second portion will be coming to the second half of the winding. Okay. So since a single winding is acting as entire transformer action, the action of a two winding transformer and auto transformer is similar. The working principle is similar, but here we are using just a single winding. So the primal losses in a transformer is Copper loss and iron loss. When load increases, copper loss will increase, and iron loss is a constant loss. Okay, iron loss is given with different names: iron loss, fixed loss, or constant loss, or magnetic losses. These losses, the iron loss is fully depending on flux reversal in a transformer, that is depending on the supply voltage. Okay, so based on supply voltage and the supply frequency, the iron loss will be occurring. Iron loss will be called as constant loss. But what is happening to the copper loss is, at initial condition, that is at no load condition, the copper loss magnitude will be very less. Since very small amount of current is passing through, the copper loss formula is I square R. You know that. Okay. So the I value, current value will be very less at starting no load condition. When load gradually increases, the no load, the copper loss also will increase. So that is one important loss in a transformer. So these two are the major losses in a transformer: copper loss and iron loss. Okay. So how much amount of power is wasted? That is what we are going to compare between two winding and auto transformer now. Okay, in two winding transformer, we will be having two different separate windings with a different thickness and a different length and different number of turns. Okay, but here we are having same amount of coil. That is, the thickness of the coil is same from point A to B, and the number of turns is also fixed in the primary side, but the secondary side it is varying. Okay. Therefore, next one is a comparison: how much amount of copper we are saving in an auto transformer. Okay, since it is very important to know, to study about the losses in a transformer, we are going to derive an equation. What is the amount of copper we are going to save in an auto transformer? Okay. Look at the first point. The weight of a copper of any winding depends on its length and cross-sectional area. So I'll ask a question with this point: what will be the thickness of secondary of a transformer, step-down transformer? Secondary winding of a step-down transformer. What will be the thickness of secondary side of a transformer? Primary, will it be bigger than the primary winding, or bigger than the, or smaller than the primary winding? The thickness of secondary winding of step-down transformer. That is, we are reducing the voltage. When you reduce the voltage, what will happen to the current? Current magnitude will increase. Keep that in mind. So when current value is increased, you need a thicker conductor. Okay, that is what you would be studying in transformation and distribution. The current magnitude depends on thickness of the conductor. Okay, we can send any amount of current to any winding, any coil, but every machine, every conductor has its own limitation. For example, if a conductor can tolerate only 15 amperes, you can send plus or minus 10%. You can send up to 17 amperes. But beyond that, when you pass the current beyond 17 amperes, the conductor will get melted. Okay, so that is where accidents are happening, electrical accidents are occurring. Okay, so in a step-down transformer, the secondary winding will be having thicker conductor compared to primary winding. So it is very evident from the first point we derived, the weight of a copper of any winding depends on its length and cross-sectional area. Also, that is what I explained, the number of turns and rated current of the winding. Okay, the weight of a copper is depending on number of turns. Look at this point. Number of turns and rated current of the winding. So cross-sectional area and rated current, these two are indirectly related. Okay, so when the cross-sectional area is very high, rated current will also be high. Also, number of turns depends, the length of the conductor depends on number of turns. So since these two are relatable to each other. So when you have more number of turns, the length of the winding will be high. When you have a thicker conductor, that is cross-sectional area of higher conductor, you can carry high rated current. Okay. So next one is, so I can write an equation. Weight of copper in section AC is proportional to, what is the current passing through winding AC, which is given as I1. Okay. Look at this point. The current passing through I1 is from A to C. So the current between A, for the point A and C is I1, and total number of turns AB is equal to, let us keep that as A. Wait, I'll write here so that you can understand. Number of turns between this like have N2 turns. So what would be the number of turns between A and C?
Nagraj sir? Hello? Hello? Hello?
What I have written here. In C is should be written N1. So the port B and C is given as Hello, hello. Can you hear now?
Yeah, sure.
I think my right, I'll take everything outside. Is the slides are visible now?
You started presenting.
And can you?
Did not. Yes, yes, it's now.
Okay. So where should I start, students? Can anyone answer where the internet got cut? Should I take the any?
Line, sir.
Hello.
Hello, next line.
Okay, okay. I'll start from here.
Okay, sir.
Also, way of upper direct proportional like number and rated current magnitude. So these two sentences are relatable to each other. Strength of any machine or any one depending on number of turns. Okay. So plus more. So that is what these two sentences are rate of in is depending number of turns and current passing through the winding. Okay, this is what yeah. Copper and for the B is into I2 one the current passing through second portion I2 minus IM. That is what connected across the load. Okay, and total use in an auto transformer. So I have to divide the auto transformer portion by portion. So initially I have taken AC and second portion is taken as BC. Now adding these, I'll get this equation. Voice not clear. Minimum, can you hear me?
Uh, Sir, now I can hear, but in between the voice is breaking. Sir, hello, hello, hello.
Okay, now?
Yeah, I can hear that. Okay.
Is it okay now? Hello?
Sir, okay.
Okay. So n1 minus n2 into I1. So after multiplying all the equations, you will get these steps. Okay, so this last line explains the total weight of copper required for an auto transformer. So this line. Okay, and next we are going to see the weight of copper used in two winding transformer. Okay, a two winding transformer is the ordinary transformer, which is otherwise called as a fixed voltage transformer. The load side will be getting fixed voltage. Okay, so in primary, we know that in the previous slide I showed you the weight of copper is depending on number of turns and current passing through the particular winding. Okay, so number of turns in the primary winding is I1, number of turns in the primary secondary is N2, current passing through the primary is I1, and current passing through the secondary is I2. So for writing both the winding of a transformer, we'll get this equation N1 I1 plus N2 I2. So after checking out the transformation ratio, N1 I1 is equal to N2 I2. So in the equation, in the first equation, both of them are equal. So I have taken that as 2 times of N1 I1. Look at this equation. So N1 I1 plus N2 I2 is written as 2 times of N1 I1. Okay. So now we are going to compare these two, the ratio between auto transformer copper weightage and two winding transformer copper weightage. So that can be written as WA. The numerator is auto transformer copper weight, and the denominator is two winding transformers copper weight. Okay. So that has been written as 2 times of N1 I1 minus N2 I1 divided by 2 N1 I1. Okay, that is what we derived in the previous sessions. And these two are getting cancelled. 2 and 2 from the numerator and denominator are getting cancelled. So we will get N1 I1 minus N2 I1 divided by N1 I1. So I'm writing that separately. N1 I1 divided by N1 I1 minus N2 I1 divided by N1 I1. So you will get 1 minus N2 into I1. Again, in this equation, I1 and I1 will get cancelled. So you will get 1 minus N2 divided by N1. Okay. So after putting the transformation ratio here, we know that N2 divided by N1 is K value. Okay. So 1 minus K, this final equation, the ratio between auto transformer and two winding transformer weight of copper is given as 1 minus K. Okay. So I can cross multiply this as WA divided by WTT. TW is equal to into 1 minus K. Okay. So multiplying that inside, I'll get WTW minus K times of W into TW. So this is the amount of copper we are saving in a auto transformer. So this is the final equation. So look at this. So an auto transformer employs only a single winding. You can save a more amount of copper. Okay, do you understand? So these are the advantages of an auto transformer. The size to power ratio is less. Okay, so in two winding transformer, can you hear my voice now? Okay, so in a two winding transformer, the size of any transformer will be bulky. For example, if it is a 1 kVA transformer, the size of two winding transformer will be high for the same rated auto transformer. The reason is it should be having two different windings wound on two different legs of a core. Okay, so we should be provide a space in between, as well as these two windings should be separately connected. So it will require a huge room for placing the conductors. Okay, but in an auto transformer, we will be having a single core and a single winding. So the size of 1 kVA auto transformer will be lesser compared to the size of two winding transformer. Okay, and it provides better efficiency. You know the reason, because the copper loss is very less. Okay, why the copper loss is very less? The reason is we are using only single winding. Okay, and it provides a better voltage regulation. You know that the voltage regulation, the reason for voltage regulation is increased resistance during loading the machine. Okay, here when you load the machine, the current passing will be limited between a range. Okay, because the entire current is depending on the source of the transformer. Okay, so it will not go beyond a limit. So the voltage regulation will be kept within a limit. Okay, so it provides a better voltage regulation for load variation. The application of auto transformer, there are plenty of applications. The auto transformers are used in starting an electrical machine. As a starters, we are using, and that we have an experiment in electrical machines lab. You will start an electrical motor slowly with the help of auto transformer. Auto transformer application can be compared with the voltage regulator which we are having in our house appliances. For example, you can check the fan regulator. What will happen if you keep the fan regulator at position 1? When you keep the regulator at position 1, the fan will be running at a slow speed. The reason is, when you keep your regulator at position 1, more amount of resistance will be connected. Okay, so when resistance are connected in a higher value, a huge amount of voltage will be dropped in the resistor itself, and only remaining part will be going to the fan coil of the fan. Okay, for example, you are applying 230 volts. Out of 230 volts, I'll be wasting 200 volts in the resistors itself. Only 30 volts will be going to the fan. So the fan will be running at slow speed. Okay, now I put the regulator in position 2. What is happening now is 2 resistors will be cut out. Only 3 resistors will be remaining in the circuit. So at that time, the resistance is reduced, so I can get a more voltage from the source. For example, now you will be getting around 150 volts. So initially you were getting 30 volts, now you will be getting 70 volts. This is for an example, don't write this. Okay, so 70 volts you will be getting, so the fan will be running at a better speed from the initial case. When you put in 3, resistance will now reduce more, so we'll be getting more voltage, the fan will be running better than that. When you keep in 5, position 5, the entire resistance connected in series will be cut out. The entire supply will be go to the fan. So now the machine, the fan will be running at its maximum speed, since it is receiving the entire power. Okay, so this is what the case of an auto transformer. When you keep the center tapping position at 0, you will be getting 0 voltage in the load side. When you adjust that to 230 maximum side, you will be getting maximum voltage. Okay, so this instrument is used wherever we require variable voltage. For example, if you want to dim a bulb, when a bulb is receiving full voltage, it will be glowing in a brighter condition. Okay, so if you want to dim a bulb, you can reduce the supply voltage by means of an auto transformer. This, as a small experiment, you can try in a laboratory. Once you come to college, you can try this. So when you, if you connect supply, auto transformer, and meters, instrument, then load. Assume, imagine this in your mind. You have a series of this connection. Okay, I'll tell one by one. First one is supply. From the auto
load. In between, you are having measuring instruments. Okay. So this measuring instruments will show you the values of current and voltage, everything. If you want to dim the bulb, brightness of the bulb, you should apply reduced voltage in the auto transformer. So auto transformer is used for wherever we require reduced voltage. Okay, and it has plenty of applications. You can go through this, and we have uploaded a document in a Google Classroom. You can even check there. Okay, so next one is three-phase transformer. With this, auto transformer part is over. So I'll repeat again so that we will continue three-phase transformer in the next class. So auto transformer, out of these topics we have covered everything. Construction of auto transformer, I told you. Principle of operation, explained you. Copper saving, we derived an equation. Application of auto transformer. Okay, so I'll go through again. Just follow my instructions. Auto transformer is a variable AC voltage transformer. So we can take the output whatever we require by adjusting the center tapping. Okay, so by adjusting this point C, we can get a different voltage ratios in the load side. Okay, and similar to all other electrical machine, auto transformer is also working under mutual inductance, that is Faraday's law of electromagnetic induction principle. And we derived an equation for copper saving in an auto transformer. So how much amount of copper is saved is W. So this is what the amount of copper we saved in an auto transformer. Okay. And these are the advantages of auto transformer. Size to power ratio is lesser. It has better efficiency. It has better voltage regulation magnitudes. And these are the applications. It is used in starters. It is used in boosters in a distribution transformer, and wherever we require controlled voltage, we can use auto transformers. Okay, so the next one is three-phase transformer. So this is the diagram. This diagram is for single-phase transformer, and for three-phase transformer, you can redraw the circuit like this. I'm taking two windings outside this and three windings outside of this. Okay, so these are the major parts. And while taking construction of single phase transformer, I told you there are more parts in an transformer. I'll explain you in while taking three phase transformer. Now I'm going to explain the parts of a three phase transformer. Okay, the major parts of a three phase transformer are, look at this diagram, the terminals are given here. A transformer core, which is very important part of any transformer. I think I have explained to the maximum of the size and everything about the core. I'll repeat it again. Okay, and windings. Core and windings are major parts of a transformer. Even without the other terminals, a transformer can work. But without core and winding, the transformer action will be failure. Okay, so do you understand? So these two, core and winding, are very important parts of a transformer. Other than that, there are some important parts which are given as transformer tank. The outer rectangular box is called as transformer tank. Oil conservator, which is here, located here, and breather. I'll mark it so that you can see. So this is oil conservator and the breather. So this is called as tank of a transformer. Bushings and terminals, connecting terminals, where we connect the input, and this is where we connect the output. Other than that, there are several parts. They are used for proper function of an auto transformer. They are used in the other parts other than core and winding. These parts are used to improve the efficiency of a transformer. Okay, let us see one by one. The first slide shows the construction of core of a transformer. We know that the core of any transformer is made up of silicon steel. Okay, so the reason for selecting silicon steel is when you use a silicon steel, the eddy current loss and hysteresis, the magnetic losses can be reduced. Okay, so when you go for a better magnetic material like silicon steel, its hysteresis loop will be very small compared to others. Okay, when the hysteresis loop is very small, that is hysteresis loop you would have studied in DCSM. If you have forgot, please go through what is hysteresis loop, and you would have studied that in physics itself, engineering physics, and other subjects also. It is a graph drawn between flux density and magnetic field intensity. Okay, so if you don't understand, I'll just give a point of it. When you increase the magnetic field intensity, flux should be increased. So that is the primal expectation. But in a magnetic core, it will not happen as we require or as we expect. It will increase initially, but when you reduce the supply voltage, it will not come to zero all of a sudden. The flux will not be zero all of a sudden. Due to residual magnetism, some magnetic property will be available in the electromagnet. Okay, even after removal of the supply, some magnetic property will be available. I explained that with an example in previous classes, like when you play with a coin and a magnet, keep the coin with the magnet for 1 or 2 days. After removing the coin from the magnet, the coin itself will be acting as a magnet. That property is called as hysteresis, residual magnetism. Okay, so if you want to make the flux around the coin nullified, that is, there should be no flux around the coil, you should keep the coin between two magnets of same poles. Okay, what will happen if you keep two magnets of same pole together? They will repel each other, so the flux in the coin will be nullified. It will be zero. Okay, so this is an example for hysteresis. So for better hysteresis loss, so for reduced hysteresis loss, we should be selecting silicon steel. And to reduce eddy current loss, we should be going for stampings, laminated structure of transformer cores. Instead of using a single core, slices of multiple core are merged together to form a single structure. Okay, so you should write about this. Okay, when you always explain about construction, first list out what are the parts in a machine. Okay, so what are the parts in a transformer? Core, winding, a transformer tank, oil conservator, breather, and there is a relay protective device. I will explain what it is later. So first list out what are the parts in the machine. Next, explain everything one by one. While explaining this, and this question will be asked for 6 marks only, so you don't need to write 3 to 4 pages. Every time I see people are writing 3-4 pages for construction. You just mention the parts, draw the diagram, write 2 points for every part of the machine. Okay, that point should be containing. First point should be about by which material it is made, and second point should be about function of it. Always write like this. Okay, so what is the core? Core is the magnetic core is used for providing magnetic path, and it is made up of silicon steel. That's all. Okay, and to reduce eddy current loss, it is made up of stampings, and to reduce hysteresis loss, a better magnetic material is used. Only 4 points are enough. Okay, you can study many things, but in examination point of view, write reduce. Well, reduce always. Okay, don't write 3-4 pages for construction alone. And second one is these are the types of transformer cores we are using. So I'll finish at 12:35, and we will go for test today. Okay, and these are the types of structure of core. Okay, we have a rectangular core, square type core, cruciform core, and 3-stepped cruciform core. Okay, which type of magnet will provide better flux around it? A circular or a rectangular? Can anyone answer for this question? Which magnet, which shape of magnet will give you a better flux? Even distributed flux. Rectangular or circular? Hello? So if you don't know the answer, I'll tell. The fourth one, the three-stepped cruciform structure. That is, it's almost looking like a circular structure. Okay. A transformer core will be providing a better flux, or any machine will be providing better flux, a uniform flux when it is round in structure. Okay, so this structure, three-stepped cruciform, is selected for higher rated transformer. Okay. And transformer tank, next one is, you know about windings. Winding is made up of copper coils. It should be having lesser resistivity so that you can easily conduct the current. And it should be, you should explain about step up and step down transformers, okay, based on number of turns in the copper winding. Okay, I'll stop with this and we'll go for the test today. I'll share the link now. I've shared the link. Please go through it and don't forget to submit. Many people are telling that I attended the exams, but I failed to submit it. Your internal marks will also be based on this. Please attend all the tests which is given to you.